Hi everyone. Let's see the implementation of Peterson solution. So I I write the algorithm which will implement the Peterson solution. Okay, and this algorithm is somewhat similar to the C programming language because in GATE syllabus we have only one programming language, which is C programming language. So based on C programming language, I write this algorithm of Peterson solution. Okay, so let's discuss this solution. First line says that hash define and2. So whenever this hash define macro expansion are given, it means that we are defining a constant value, and this constant value is particularly constant throughout the whole program. Okay, so and2 indicates number of processes. And2 means there are two processes used by this solution, process P0, P1, or either process Pi or process Pj. Second line is hash defined true as 1. So it already defined that true means 1. So whenever you are considering the particular word true, then it means it indicates value 1. Similarly, it defined hash defined false as 0. So for false, we are using 0 as constant value. Now after that, we are using two variable in the Peterson solution. One is interested variable and other is turn variable. At the initial point, at the starting of the particular solution, interested variable is set to be false. Okay, that means it takes 0 as a value, and here in bracket n is given and indicates the number of process. If n is 0, then it means process P0, it represents process P0. If n is 1, then it represents process P1. Okay, so at the starting point of the algorithm or particular this implementation, both interested 0 as well as, so I will write it the full name so that you will not confused between interested variable and interested integer data type. Okay, so interested of 0 as well as interested of 1 is false at the starting point. Okay, so initially both the processes are not interested in entering the critical section, and we are defining one more variable, which is turn variable. Okay, and if you see that two variables, these two variables are declared before the before any function. Here we are using two functions. One is entry function and one is exit function. Entry function represent the entry section of the critical section, and exit function represent the exit section after the critical section. Okay, so turn and interested variable are defined above the function, that it means it is global variable. Both interested as well as turn are global variable. So this variables is used by either entry function or it is used by either exit function. Okay, in entry function. Okay, so you already know that before critical section we have entry section, and after the critical section we have exit section. So we make a code for entry section and we also make a code for exit section. Okay, for entry section the code is void entry, which means it does not return anything to the particular user who calls this function, and it takes process. Here int process means whether process P0 is considered or process P1 is considered. So based on this, so here process represent number. If it is 0 means process P0, if it is 1 means process P1. Then in the entry function we are defining a local variable int other represent the other process. Means if it is here 0, so this function takes process P0 for executing the entry section code, and other represent the process P1. Okay, so here other is 1 minus process, other is equal to 1 minus process. If it is process P0, then other will be 1 minus 0. 1 minus 0 will be process P1, 1. And if it is process P1, so here value will be 1, then other will be 1 minus 1. 1 minus 1 will be 0, means process P0. So based on that we can calculate the other value, and after that it is interested of process is equal to true. It means that this particular entry section makes this process their interested variable as true, which means this particular process is interested to enter into the critical section. Got it? Now after that, turn is equal to process, and we also set the turn of this process so that no other process will claim that it is their own turn to get into the critical section. So we are actually providing a cover to the process by two ways. One is interested and the other one is turn. Okay, so this particularly cover make them stronger and make them the right candidate to get into the critical section. Got it? And after that, we are checking the condition by using while loop. Interested of other equal to true means we are checking whether before my setting interested as true, can anyone who set prior their interested variable as true. If anyone set prior interested as true, then I will stuck myself in the while loop and got into infinite loop. Okay, so interested of other equal to true and turn equal to process. Okay, if this condition fails, then we will successfully enter the critical section. Okay, and use this particular shared resource or critical section. And after using this shared resource or critical section, after whenever we are leaving the critical section, then in the exit section itself or in the exit function itself, we are making our interested variable as false. Okay, so if you see them, this is the main hurdle or barrier which both process have to be qualified. If any one process does not pass this hurdle while loop, then they will not get a chance to enter into critical section. Got it? So here our two primary requirement and two secondary requirement both are achievable. One is mutual exclusion. Yes, mutual exclusion is guaranteed. The other one is progress. Progress is also guaranteed. Bounded weighting is also guaranteed. And the last one is architectural neutrality. We already seen that it is also provided. So all the requirement of synchronization mechanism is provided by this Peterson solution. So if we are talking about busy waiting solution, if we have a criteria to implement a solution which is busy waiting, then we prefer Peterson solution, because Peterson solution is superior to all of the busy waiting solution available right now. Okay, and it is a very good solution. Okay, now if you trace the particular solution, you can trace it. Let's try one trace here. Let's take a process P0. Let's say I have numbered this here line 1, 2, 3, 4, 5, and it is line number 6. So line number 1 to 5 is present in entry section, and line number 6 is present in exit section, and all the other codes are irrelevant, because for tracing the particular solution we are using this particular line of code. Okay, so let's say process P0 enter into critical section. It executes the entry function first. So it will make interested of int of other, then other is equal to 1 minus process, means other is process P1, then interested of process is equal to true. It will make its interested as true. It will make its adds turn as process P0, and it will execute the line number 5. Line number 5 says process P1 does not set its interested variable, and also it does not set its turn variable. So it will successfully pass the while loop and enter into critical section. Now whenever process P1 wants to enter the critical section, it does not enter. Why? Because at line number 5 it will pass line number 1, 2, 3, 4, but at line number 5 it will got stuck in and it will fall in infinite. So we can easily see that only one process can enter into critical section, so mutual exclusion is provided. If process P0 leaves the critical section, means it will execute line number 6, then after that process P1 enter the critical section by executing line number 5, and then after critical section, and then after line number 6. So progress is also guaranteed here. Okay, and bounded waiting is also guaranteed here. Bounded waiting means no other process, there are only two processes here, So no other process should wait for a long time to get their chance to enter into critical section. So definitely bounded waiting is guaranteed, and it is a software mechanism, so it provides architecture neutrality. Okay, so you can practice, or you can trace out some sequence like this to get clear understanding about the Peterson solution. Okay, I am leaving it to you. So in the next video we will start the next synchronization mechanism classification, which is without busy waiting. So after this particular Peterson solution, we are discussing all the solutions which are present in the category of without busy waiting.